Welcome back to the deep dive. Today, we are doing something a little bit different. We usually look at things happening, to the world or to the body, but today we are taking a journey into the very blueprint of human life itself. We often think of disease as an invader, a bacteria, a virus, a car crash, some sort of physical blow. But what happens when the pall is coming from inside the house?
It's a really fundamental shift in perspective, isn't it?
Yeah.
They're moving away from this idea of disease as just an external assault and looking at it as a problem of information management gone wrong.
Exactly.
The body is, at its core, built on a set of instructions.
And when those instructions have typos or, I don't know, missing pages or they're written in invisible ink, things go wrong. For this deep dive, we're synthesizing two absolute titans of medical literature.
The big ones.
We have the systems framework from Robbins and Cotran Pathologic Basis of Disease, specifically the chapter on genes and human diseases. And we're pairing that with the mechanistic, really grounded insights from Underwood's pathology, focusing on their chapters about what causes disease and disorders of growth.
It's a powerful combination. It really is. Robbins gives us that sweeping, sort of unifying view of how genetic errors manifest across whole organ systems. The clinical pathological integration.
The big picture.
The big picture.
Uh-huh.
But Underwood, on the other hand, is just fantastic at grounding us in the why.
Yeah.
It treats disease not just as a list of symptoms, but as a cellular response to dysregulation. It's down to the nuts and bolts.
Right. And before we dive in, a quick disclaimer for you listening, especially the medical students in the crowd. This is a conceptual map. We are connecting the dots. We're interpreting the synthesis of these texts. This is not a substitute for sitting down and actually reading the chapters in Robbins and Underwood.
Absolutely not. Please read the books.
Reading the original text is essential for your education.
Absolutely. Consider this the scaffold. We're building a framework so that when you read, you can hang all that detailed knowledge on it later.
So our mission today is to explore how these inherited instructions shape risk long before any illness actually appears. And there is this central tension I want to unpack right at the start.
Okay.
We usually hear it's genetic and we think it's inevitable. This concept of genetic destiny.
Which is a very fatalistic way to look at your own biology. It sort of removes all agency.
Right. But looking at these texts, it seems like the reality is much more about biological probability. Is a mutation a guarantee, or is it just a loaded die?
That is the perfect question to frame this entire discussion. And as we're going to see, it really varies. Sometimes a mutation is a sentence written in stone. If you have the gene, you will get the disease. But so often, especially with the complex diseases that Robbins describes, like diabetes or heart disease, it's just shifting the odds. It's the difference between, say, a blueprint that's missing a load-bearing wall and a blueprint that just suggests using slightly cheaper wood for the framing.
I love that analogy.
One collapses immediately, the other might hold up just fine unless, you get hit by a hurricane.
That's brilliant. Okay, let's look at the roadmap. We are going to start small, literally microscopic, with the mechanics of mutations. Then we'll look at the rules of the game, how these errors get passed down through families.
The inheritance patterns.
Exactly. Then we'll look at what happens when the building blocks themselves fail, what happens when the chemical workers inside the cell go on strike, and finally we'll look at the rule breakers, those genetic conditions that just defy standard logic.
Sounds like a plan.
All right, let's start with the nature of the error itself. Underwood makes a distinction right off the bat between inherited and acquired abnormalities. This seems basic, but it changes everything about how we look at a patient.
It really does. It's a fundamental split. So Underwood classifies genetic abnormalities into germline and somatic. Germline mutations are the ones you inherit. They are present in the egg or the sperm that made you.
So from day one.
From before day one. It means every single cell in your body, from your hair follicles to your liver cells, carries that error. You are, in a sense, built from that error.
Versus somatic mutations, which are acquired.
Exactly. Somatic mutations happen later. They happen in a single cell line after you're already built. Maybe a skin cell gets hit by too much UV radiation, or a lung cell gets exposed to cigarette smoke.
This is cancer, basically.
This is the basis of most cancers, yes. It's a local rebellion. But for the most part today, we're talking about those germline, inherited instructions that define the entire organism from the get-go.
So Robbins defines a mutation simply as a permanent change in the DNA. But not all changes are created equal, right? There are typos, and then there are, disasters.
Right. And we can categorize them by the scale of the damage. At the most basic level, you have what are called point mutations. This is where a single letter of the DNA code, a single nucleotide, gets swapped for another one.
And even there, the outcome depends on what that swap actually does, because the code has some redundancy built in, doesn't it? Sometimes a swap doesn't matter.
That's what we call a silent mutation. The code is degenerate, so different three-letter words can code for the same amino acid. But Robbins breaks down the ones that do matter into two main types: missense and nonsense mutations.
Okay.
A missense mutation is when that letter swap changes the instruction for which amino acid gets put into a protein.
And amino acids are the building blocks of proteins. So if I swap a letter, I might swap out a red Lego brick for a blue one.
Exactly. Now, if the blue brick is the same shape and size as the red one, we call that a conservative missense mutation. The protein might still work okay. It's a little bit wonky, but the wall still stands.
But if you swap that brick for, I don't know, a piece of jelly.
That's a non-conservative mutation. The structural integrity is just gone.
And the classic example here is sickle cell anemia. It is just mind-blowing to me that such a massive, painful, systemic disease comes down to one single letter.
It is terrifyingly simple. In the beta-globin chain of hemoglobin, a single nucleotide changes from a T to an A. CTC becomes CAC. This causes a switch from glutamic acid to the amyline at the 6th position in the protein chain.
And why does that specific switch matter so much? What's the chemistry going on there?
It's all about water. Glutamic acid is hydrophilic. It loves being in water. Valine is hydrophobic. It hates water. It wants to get away.
Okay.
So you have this hemoglobin molecule floating inside the red blood cell, which is mostly water. When it's carrying oxygen, it's fine. The shape is stable. But when the oxygen level drops, like in a small capillary, that valine spot becomes exposed and sticky. It wants to hide from the water.
So it sticks to another hemoglobin molecule.
It sticks to the valine on the next hemoglobin molecule, which is also trying to hide. They start to clump together.
They polymerize.
They polymerize. They form these long, stiff, crystal-like rods inside the red blood cell. And these rods physically stretch the cell into that characteristic sickle shape.
And those stiff sickle cells get stuck in the small blood vessels.
Exactly. They block blood flow.
Yeah.
That's what causes the excruciating pain crises. That's what causes the tissue damage and the organ failure. All because valine hates water and glutamic acid loves it. One single letter.
That's missense. You also mentioned nonsense mutations. That sounds less severe, maybe just annoying. Is it dangerous?
It's usually much worse. A nonsense mutation changes the codon for an amino acid into a stop codon.
So it's like putting a period in the middle of a sentence.
Exactly.
Yeah.
The cellular machinery is reading the instructions, building the protein chain, and suddenly, stoppy, full stop. The protein gets cut short, it's truncated.
And what does the cell do with half a protein?
Usually it recognizes that this is garbage. It's a non-functional, potentially dangerous fragment. So it destroys it entirely through a process called nonsense-mediated decay. Robbins uses beta thalassemia as a great example of this. You just end up with a complete deficiency of the beta-globin protein because the instructions effectively just stop halfway through.
So we have letter swaps, but Robbins also talks about deletions and insertions. And this is where the reading frame concept comes in. This always trips people up. Can you explain the famous "the cat ate the rat" analogy?
Sure. Think of our DNA being read in three-letter words called codons. We'll use English to make it simple. The cat ate the rat. All three-letter words. It makes perfect sense.
Okay, I'm with you.
Now imagine you delete just one letter, say the C, from the word cat. You don't just lose the word cat. The entire reading frame shifts to the left. The cell still reads in groups of 3.
So instead of the cat ate, it would read the Ada tet her.
Total gibberish. Immediately. That is a frame shift mutation. Everything downstream of that one-letter deletion is now completely wrong. It's not just one bad brick in the wall. The entire rest of the wall is built out of nonsense.
And this happens in real diseases.
Absolutely. A prime example Robbins gives is Tay-Sachs disease. In the Ashkenazi Jewish population, a common mutation is a 4-base insertion in the XXA gene. That small insertion throws off the reading frame, the protein becomes gibberish, and the result is a truly devastating neurological disease.
It's wild to think that our health literally hangs on such precise accounting. But I want to pivot for a second to something Underwood brings up that I found really profound. We're focused on the genes, but Underwood highlights this nature versus nurture debate with a fascinating thought experiment from an epidemiologist named Jeffrey Rose.
Ah, yes, the smoking hypothesis. This is a brilliant way to understand why we sometimes miss genetic factors, or, on the flip side, why we sometimes miss environmental ones.
So what's the idea?
Rose proposed this. Imagine a society where everyone, men, women, children, everyone smoked 40 cigarettes a day. It's just a cultural norm, like breathing air or drinking water.
Okay, a terrible place to live, lots of coughing, but I'm following.
In that society, lung cancer would still happen, but not everyone would get it. Some people would get it at 40, some at 80, some might never get it at all. Since the environment, the smoking is constant for every single person, the only variable left to explain a difference in who gets sick is
Genetics.
genetics. So the researchers in that world would look at all the data and they would say, aha, lung cancer is a genetic disease. It runs in families.
They would completely miss the cigarettes because it's the background noise.
Precisely. They would find the genes that make you susceptible to smoke damage. They would ignore the smoking itself because everyone does it. They would conclude that lung cancer is 100% genetic disease.
But we, in our world, know that if you just took away the cigarettes, the disease would almost vanish.
Correct. And Underwood uses this to illustrate a really important point. Genetic factors are easiest to spot when environmental factors are uniform or absent. But in the real world, it's always a messy mix of both. It challenges us to ask, what universal smokers are we living with today?
That's a heavy thought.
Is it our diet? Is it our stress levels? Are we calling some things genetics just because we're all living in a universally stressful or toxic environment?
And Underwood doesn't stop there. It doubles down on this with the Barker hypothesis. This kind of flips the script entirely. It suggests the environment in the womb, specifically nutritional deprivation, can program the fetus for disease decades later.
Yes, fetal programming. It's a fascinating and frankly a bit scary concept. Imagine a fetus developing in a mother who isn't getting enough nutrition. The fetus is smart. It adapts.
It prepares for the outside world.
It prepares. It says, okay, the world out there is scarce. I need to build a metabolism that hoards every single calorie it can find. I need to be thrifty.
Survival mode.
Exactly. It alters its epigenetic settings, the way its genes are expressed, to maximize energy storage. But then that baby is born. And let's say they're born into a modern Western society with fast food on every corner and an abundance of calories.
So they are programmed for a famine, but they find themselves living in a feast.
And that mismatch is a disaster. That thrifty programming, which was a brilliant survival adaptation, now leads to rapid obesity, hypertension, insulin resistance, and heart disease. The software was written for a completely different hardware environment. It's a perfect example of how nurture, the womb environment, affects the expression of nature for the rest of your life.
So we have the mutations and we have the environment. Now let's talk about how these mutations actually travel through families. We're getting into the rules of the game classic Mendelian inheritance.
The classics: autosomal dominant, autosomal recessive.
But before we even define those, we need to clear up two terms that Robbins is really insistent on: penetrance and expressivity. They sound similar, but they describe very different realities for a patient.
They do, and it's crucial to get them straight. Think of penetrance as a light switch. It is a simple yes or no question. If you have the mutation, do you show any signs of the disease? Yes or no?
So if 100 people have the gene and only 50 of them get sick?
That's 50% penetrance.
Yeah.
It's like having a loaded die that, for whatever reason, doesn't always land on 6. You have the gene, but for some reason, maybe other protective genes you have or a beneficial environment, the light switch stays off. That's incomplete penetrance.
Okay, so penetrance is the on-off switch. What's expressivity?
Expressivity is the dimmer switch.
The volume knob.
Right. The light is definitely on. You have the disease. The penetrance is 100%. But how bright is it? How severe is it? Robbins uses neurofibromatosis type 1 as the classic example here.
Okay.
You might have a parent who just has a few light brown spots on their skin cafe au lait spots.
Yeah.
And maybe some freckles in their armpits. They are technically affected. They pass the gene on to their child.
And a child gets the exact same mutation.
The exact same mutation. But that child might have severe skeletal deformities, massive benign tumors growing on their nerves, learning disabilities, and a higher risk of cancer. Same gene, same mutation, but vastly different expressivity.
That must be terrifying from a genetic counseling perspective. You can tell a family the gene is there, but you can't tell them if it's going to be a minor nuisance or a life-altering catastrophe.
Exactly. It makes predicting the future very, very difficult.
Okay, with that in mind, let's unpack autosomal dominant, or AD. The key here seems to be that you only need one bad copy of the gene to get sick.
That's right. Heterozygotes are affected. And Robbins makes a really insightful point about what kind of proteins are usually involved in autosomal dominant diseases. They tend to be structural proteins or receptors.
Why is that? Why not enzymes?
It comes down to two main mechanisms: haploinsufficiency and the dominant negative effect.
Okay, let's break those down. I found haploinsufficiency really interesting because it sounds like a supply chain problem.
That's a great way to put it. Haplo means half. Insufficiency means not enough. So quite simply, making 50% of the normal protein isn't enough to do the job properly.
The system can't run on half capacity.
Right. A great example is familial hypercholesterolemia. You have 2 copies of the gene for the LDL receptor. Think of it as the glove that catches bad cholesterol from the blood and pulls it into the liver. If 1 copy of your gene is broken, you only made half the number of gloves.
And half the gloves can only catch half the cholesterol.
So the rest of it just stays in your blood, building up in your arteries. You are haplo-insufficient. 50% is not enough.
Okay, that makes sense. And the dominant negative effect. This is the one that always feels a little bit spiteful to me.
That's the one bad apple spoils the whole barrel scenario. This happens a lot with big structural proteins like collagen. Collagen isn't just one chain, it's a trimer. It's made of 3 separate protein chains braided together like a rope.
Okay, so imagine 3 strands braiding together to form a strong rope.
Now, if you have 1 mutant gene, roughly 50% of your individual strands are going to be defective. But they don't just float away and mind their own business. They try to braid into the rope along with the good ones.
And if you try to make a rope with a rotten thread?
The whole rope is weak. It snaps under pressure. Even if you have perfectly good strands, if they are physically tethered to a bad strand, the entire structure fails. In fact, statistically, if half your strands are bad, only about 1/8 of your final collagen ropes will be made of purely good strands. The rest are compromised.
So the bad protein actively sabotages the good one.
It actively interferes. That's why these structural diseases are so often dominant.
So that's a sharp contrast with autosomal recessive or AR. These are the conditions where you need 2 bad copies. You have to get 1 from mom and 1 from dad.
Correct. And these almost always involve enzymes.
Metabolic workers of the cell.
Exactly. Let's go back to our factory analogy. Let's say you have an enzyme that breaks down a specific type of cellular waste. If you have 1 working gene and 1 broken, when meaning you're a carrier, you're making 50% of the normal amount of that enzyme.
Is that enough?
Usually, yes. Enzymes are incredibly efficient catalysts. Even at 50% capacity, they can typically keep up with the workload and clear the backlog of waste. The factory might run a little bit slower, but the trash doesn't pile up to toxic levels.
So you don't get sick. You're an asymptomatic carrier.
Right. You only get the disease if both of your workers call in sick if you inherit 2 broken copies. That's why recessive disorders often appear to skip generations. The parents are perfectly healthy carriers, and they might not even know they have the mutation until they have a child who inherits both bad copies.
And this is where Robbins points out that consanguinity-like cousin marriage increases the risk.
It does, because relatives are much more likely to carry the same rare recessive mutation that they inherited from a common ancestor.
Then we have X-linked disorders involving the sex chromosomes.
Right. So males are XY, which means they are homozygous for almost all the genes on the X chromosome. They don't have a backup copy like females do.
So if there is a recessive mutation on their one and only X chromosome,
they get the disease. The default is that females with their 2 X's are carriers. But, and this is a big but, Robbins brings up the lion hypothesis. This suggests that females aren't just simple protected carriers.
This is the idea that one X chromosome gets shut down.
Exactly. It's a crucial concept.
Yeah.
In every cell of a female during early development, one of the 2 X chromosomes is randomly inactivated. It shrivels up into a little dense spot called a bar body.
So a woman is actually a mosaic of her 2 X chromosomes.
Yes, she's a patchwork quilt. In some patches of her body, the X she got from her dad is active. In other patches, the X she got from her mom is active. The classic visual is a calico cat. Their coat pattern is a direct result of X inactivation.
Does this actually matter for human disease?
It can. Usually the random 50-50 mix protects her. If half her liver cells have the bad gene active, the other half are healthy and they can pick up the slack. But, and this is the kicker, if she gets what's called unfavorable skewing or skewed X inactivation.
Meaning she just gets unlucky with the coin flip.
Right. If by sheer bad luck, the healthy X chromosome gets turned off in, say, 90% of a critical tissue cells, she can actually start to show symptoms of an X-linked recessive disease. Even though she has a perfectly healthy gene, she becomes a symptomatic carrier.
That's fascinating. It really blurs the line between being a carrier and being affected.
It reminds us that genetics is rarely a simple binary. It's almost always a spectrum.
Let's move to section 3. When the structure fails. We talked about how structural proteins are often implicated in autosomal dominant diseases. Let's look at the specific examples Robbins highlights. I want to start with a mental image.
Yeah.
Imagine a basketball player. 6'8", incredible wingspan, long, thin fingers. He's an amazing athlete, a star on the court, but one day, during practice, he just collapses on the floor.
That is the tragic and all too common classic presentation of an undiagnosed case of Marfan syndrome.
Marfan is a defect in the FBN1 gene, which makes a protein called fibrillin-1.
Fibrillin, think of it as the scaffolding for elastin. Elastin is the protein that gives tissues their stretch and recoil like a rubber band. Fibrillin organizes the elastin fibers. You find it in the skin, the lungs, and most critically, in the wall of the aorta.
But Robbins emphasizes that it's not just about having weak or stretchy tissue, there's a signaling problem going on too.
This is the real aha moment in understanding Marfan. Fibrillin has a second job. It sequesters, or, it puts handcuffs on a growth factor called TGF-beta.
So normally fibrillin's job is to keep TGF-beta quiet and under control.
Exactly. But in Marfan, the fibrillin is defective. The handcuffs are broken and they fall off. So you have way too much active TGF-beta floating around in the tissues. And what does TGF-beta do? Among other things, it tells bones to grow.
And that explains the skeletal features, the tall stature, the arachnodactyly, the spider fingers. It's not just that the tissue is stretchy, it's that the growth signals are just screaming, "Grow!" because the silencer protein is broken.
Precisely. It perfectly explains the bone overgrowth. But the absolute killer in Marfan syndrome is the aorta.
The cardiovascular system.
The aorta is the massive artery coming off the heart. It needs to stretch and recoil with every single heartbeat, 60 times a minute for an entire lifetime. Without proper fibrillin, the wall of the aorta loses that crucial elasticity.
Okay.
But worse, the excess TGF-beta causes inflammation and the degradation of the tissue in the aortic wall. Robbins calls it cystic medial degeneration.
That sounds ominous.
It means the middle layer of the aortic wall, the media, essentially turns to mush. It gets weak and cystic. And eventually, under the constant pressure of blood flow, it starts to stretch out like an overblown balloon. That's an aneurysm.
Then if that aneurysm tears?
That's an aortic dissection. The layers of the aortic wall rip apart. It's a catastrophic, often fatal event. And that's the tragedy of Marfan. Often the very first symptom is sudden death from a dissection if it isn't diagnosed early. That's why recognizing those physical signs, the long fingers, the pigeon chest, the lens dislocation in the eye, is literally life-saving.
Then we have the other side of the structural coin, Ehlers-Danlos syndromes, or EDS.
Right. EDS is actually a whole group of different disorders, but they all center on the protein collagen. If fibrillin is the elastic recoil, collagen is the tensile strength. It's the steel rebar in the concrete. It stops tissues from tearing apart.
And without it.
Things are too stretchy, but they aren't strong. You get hyperextensible skin, you get hypermobile joints. These are the people who can be contortionists. But their tissues are incredibly fragile. Robbins describes the cigarette paper scars. If you try to stitch up a wound, the stitches might just rip right through the skin because the collagen can't hold the tension.
And while most forms of EDS are autosomal dominant, because it's a structural protein, there's a specific type Robbins mentions that breaks the rule we just learned.
Yes, the kyphoscoliosis type. This is a really interesting exception that proves the rule. It's caused by a deficiency in an enzyme lysyl hydroxylase. This enzyme's job is to add hydroxyl groups to collagen, which allows it to form strong crosslinks.
So the collagen protein itself is being made just fine, but the worker that's supposed to weld it all together is missing.
Exactly. And because it's a defect in an enzyme, it follows an autosomal recessive inheritance pattern, even though the final result is a structural failure of collagen. It results in a severe curvature of the spine kyphoscoliosis and fragility of the eye. It's a perfect illustration of how knowing the specific molecular mechanism can tell you the inheritance pattern.
Okay, let's move on to section 4, the metabolic logjam. We touched on familial hypercholesterolemia, FH, earlier as a receptor defect. But I want to really dig into the numbers here because they explain why this is such a major public health issue.
They are staggering. In a heterozygote, that's someone with one bad copy of the LDL receptor gene, the blood cholesterol levels are 2 to 3 times higher than normal. These people look and feel perfectly healthy, but their arteries are quietly clogging up with cholesterol from birth.
And they can have heart attacks very young.
Very young. It's not uncommon for them to have their first heart attack in their 30s or 40s. And this is one of the most common genetic disorders, affecting about 1 in 500 people.
But then you have the homozygote, someone who was unlucky enough to get 2 bad copies.
Right. They have almost no working LDL receptors. None. Their cholesterol is 5 to 6 times normal. We were talking about levels of 600, 800, even 1,000 milli-GDL.
And where does all that cholesterol go?
It has to go somewhere, so it deposits in tissues. You see these xanthomas, these yellow, fatty bumps on their elbows, their knees, their tendons. But most dangerously, it deposits in their arteries, causing severe atherosclerosis at an incredibly young age.
And the heart.
They can have myocardial infarctions, heart attacks, before the age of 20. There are recorded cases of 5-year-olds with fatal heart attacks from homozygous FH. It's a stark, brutal example of how a single genetic instruction directly dictates a clinical outcome.
Now let's switch from receptors to enzymes and look at the lysosomal storage diseases. I want to paint a picture here. Imagine a busy, functioning city, but suddenly the garbage collectors that are responsible for picking up specifically plastic go on strike.
That's a great analogy. The lysosome is the cell's recycling center, or its stomach. It contains dozens of different specialized enzymes, and each one is a specialist designed to break down one specific type of waste.
So in your city analogy, paper is still being recycled, glass is being recycled, food waste is being composted, but the plastic, it just sits there.
And it piles up. First, the bins are full. Then the streets are full of plastic bags. Then it starts piling up inside people's houses. In the cell, this plastic is the substrate, usually a complex fat or a sugar. If the specific enzyme that degrades it is missing, that substrate just accumulates inside the lysosome.
And the lysosome itself gets bigger and bigger.
Massive. The lysosomes swell up with undigested material, crowding out all the other organelles in the cell. Eventually, the cell's normal function shuts down, or in many cases, the cell dies.
Tay-Sachs is probably the most well-known of these. Let's walk through the clinical reality of that disease.
It is a heart-wrenching disease. The missing enzyme is hexosaminidase A. The trash that piles up is a specific lipid called GM2 ganglioside. And the tragedy of Tay-Sachs is where it piles up.
In the neurons.
In the neurons of the brain and the retina. A baby with Tay-Sachs appears perfectly normal at birth. But over the first few months, as these gangliosides accumulate, the neurons begin to swell and die. The baby stops hitting developmental milestones. They lose the ability to roll over, to sit up, to see, to hear.
And Robbins describes the famous cherry red spot on the retina. Why is it red?
It's actually a contrast effect. The ganglion cells surrounding the macula of the retina become stuffed full of these white, fatty gangliosides. So the whole retina looks pale or white, but the fovea, the very center of your vision, doesn't have those ganglion cells. So you're seeing through to the normal red-colored choroid layer underneath. It looks like a bright red spot against a pale background.
And Robbins mentions this involves something called the unfolded protein response. It's not just the cell getting crowded with junk, is it?
No, it's more active than that.
Yeah.
The mutant hexosaminidase, a protein, is often misfolded. The cell's quality control machinery detects this as a crisis. It triggers the unfolded protein response, which basically says, we are making garbage here, shut down production. If the stress is too high and can't be resolved, the cell triggers apoptosis.
It commits suicide.
So the neurons aren't just getting clogged, they're actively killing themselves in an attempt to protect the organism from these misfolded proteins.
And there are others in this family of diseases too, Niemann-Pick and Goucher.
Briefly, yes. Niemann-Pick types A and B are due to a deficiency in an enzyme called acid sphingomyelinase, so sphingomyelin accumulates. Type A is severe and involves the brain, leading to neurodegeneration. Type B mostly affects the organs, causing a massive liver and spleen.
And Goucher.
Goucher disease is actually the most common of these lysosomal storage disorders. It's a defect in the enzyme glucocerebrosidase. The waste product, glucocerebroside, piles up.
And what are the Goucher cells? I remember seeing pictures of those.
Those are macrophages, the big immune cells that go around eating cellular debris. In Goucher disease, they eat the waste, but they can't digest it. So they become absolutely stuffed with undigested glucocerebroside. Under a microscope, their cytoplasm gets this classic crinkled tissue paper or wrinkled silk appearance. It's a hallmark pathology image.
Okay, we've covered the standard rules of inheritance. Now let's get to my favorite part, Section 5, breaking the rules. Non-classical inheritance. This is where things get really weird. This is where Mendel's P's just don't explain what we see in the clinic.
This is where modern genetics gets really interesting. It forces us to rethink what a gene even is and how it can behave.
First up, trinucleotide repeat mutations, the stuttering genes.
Right. Imagine a gene that has a short, repeated DNA sequence, let's say CGG, CGG, CGG. In most normal people, that sequence might repeat, say, 20 or 30 times. It's stable. But in these conditions, that region of the DNA becomes unstable. It's slippery.
Slippery? What do you mean by that?
When the DNA is being copied during cell division, the machinery that does the copy in the DNA polymerase can sort of slip When it gets to this repetitive part, it can lose its place and accidentally copy the same section twice, creating a little loop, so 30 repeats might become 40. Then in the next generation, 40 might become 80.
And this expansion leads to a phenomenon called anticipation.
Yes, this is a key feature. It means the disease tends to get more severe, or it starts at a younger age, in each successive generation. The stutter just grows longer and more unstable with every copy.
Fragile X syndrome is the big one here. But there is a nuance in Robinson I think is absolutely critical. We usually think more repeats equals more disease, but Fragile X has this really weird paradox involving what's called the premutation.
This is a fascinating and complex mechanism. So Fragile X is caused by a CGG expansion in a gene on the X chromosome called FMR1. If you have the full mutation, meaning over 200 of these CGG repeats, the cell body panics. It looks at this massive, unstable stutter and says, this is dangerous, we have to shut this down.
So it silences the gene.
It silences the gene completely using methylation. It basically cements that part of the chromosome shut. No messenger RNA is produced, therefore no FMRP protein is made. And it's this lack of the FMRP protein that causes the symptoms of Fragile X. The intellectual disability, the long face, the large ears, the macroorchidism.
Okay, so full mutation equals gene silencing equals no protein equals Fragile X syndrome. But what about, say, the grandfather of that affected boy? The man who has maybe 100 repeats, he's in the premutation range.
Right. For years, he was thought to be an unaffected carrier. He doesn't have Fragile X. His gene isn't silenced. In fact, the exact opposite is happening. The gene is still open for business, but the cellular machinery really struggles to read through that long, stuttering repeat section. It actually produces too much messenger RNA.
It goes into overdrive trying to read this difficult passage.
Exactly. And this excess abnormal messenger RNA is toxic. It clumps up in the nucleus of the cell and traps other important proteins, gumming up the works. So these men, who we used to tell were completely fine, can actually develop a totally different disease later in life. It's called Fragile X-associated tremor ataxia syndrome, or FXTS. They get tremors, balance problems, and Parkinsonism.
That is just wild. So the full mutation causes disease through an absence of protein, loss of function, but the premutation causes a different disease through an excess of toxic RNA, a toxic gain of function.
Exactly. It completely changed how we had to counsel these families. We used to tell these grandfathers they were just carriers. Now we have to tell them that they themselves are at risk for a progressive neurodegenerative condition.
What about Huntington disease? That's also a trinucleotide repeat disorder.
Yes, but it's a bit different. In Huntington, the repeat is CAG, and it's located inside the actual coding region of the gene. So the repeats get translated into the protein. They create a protein with a long, sticky tail of glutamines. This mutant protein folds wrong, clumps together into aggregates, and is directly toxic to neurons, specifically in a part of the brain called the caudate nucleus. It's a classic, tragic example of a dominant toxic gain of function.
Okay, next rule breaker, mitochondrial inheritance.
The powerhouse of the cell has its own DNA, a tiny circular genome with just a handful of genes. But here's the catch. All of your mitochondria come from your mother's egg. The sperm contributes its nuclear DNA, but almost none of its mitochondria make it into the embryo.
So mitochondrial diseases can only be passed from a mother to her children.
Correct. An affected mother will pass it to all of her children, both sons and daughters. But an affected father passes it to none of his children. It's a very distinct inheritance pattern.
But explain the concepts of the bottleneck and heteroplasmy. Why is it that one sibling can be severely affected by a mitochondrial disease and another sibling can be barely affected at all, even with the same mother?
This comes down to the threshold effect. So a single cell has hundreds, even thousands, of mitochondria. In a person with a mitochondrial disease, some of those mitochondria might have the mutation, but some will be normal. It's a mixed population that's heteroplasmy.
Okay.
Now, when the mother makes an egg, she doesn't carefully count out the mitochondria. She just puts in a random handful. It's like reaching into a big jar of mixed red and blue jelly beans and grabbing a scoop. One egg might, by chance, get a scoop that is mostly bad red jelly beans. Another egg might get a scoop that's mostly good blue ones.
So it's a random sampling error at the level of the egg cell.
Exactly. This bottleneck during egg formation means the proportion of mutant DNA can shift wildly between generations and even between siblings.
And the disease only actually shows up if the number of bad mitochondria in your tissues crosses a certain threshold.
Right. If only 20% of the mitochondria in your muscle cells are bad, the other 80% can compensate and you might feel fine. But if 80% are bad, the cell's energy production plummets and you get symptoms.
And which organs fail first?
Yeah.
The ones that are the most energy hungry.
The brain, the heart, the muscles.
Exactly. Leber hereditary optic neuropathy, or LHON, is the classic example. It causes progressive blindness because the optic nerve is an extremely high-energy demand tissue. If the power plant starts to flicker, the brightest lights in the house go out first.
All right, our last rule breaker. Genomic imprinting. This one still blows my mind. We are taught in high school biology that it doesn't matter if a gene comes from your mom or your dad. A gene is a gene. But for a small number of imprinted genes, it matters immensely. For these genes, the copy you inherit is stamped with an origin tag. It's biologically marked as being either paternal or maternal.
Like a property of dad sticker on it.
Yes, exactly. They are silenced or imprinted via methylation based on which parent they came from. So for a given imprinted gene, you only ever use one of your two copies.
And the classic detective story here is the duality of Prader-Willi and Angelman syndromes. Let's set the scene.
Okay. Imagine two different children enter your clinic. Child A has Prader-Willi syndrome. They have some intellectual disability. They're short, they have small hands and feet, and they have this terrifying, insatiable drive to eat. They never, ever feel full. It leads to morbid obesity.
Okay.
Child B has Angelman syndrome. They have severe intellectual disability, but their presentation is completely different. They have a happy, excitable demeanor, often with inappropriate laughter. They have jerky, puppet-like movements, ataxia, and seizures.
So two totally different clinical pictures.
Totally different. But when you look at their DNA, you find that they often have the exact same deletion on chromosome 15. A chunk of the long arm, region 15q12, is just missing.
How is that possible? The same deletion causing two completely different diseases.
It all depends on whose chromosome got deleted. In this specific region of chromosome 15, there are some genes that are only active on the paternal copy you inherit. The maternal copy of those same genes is naturally silenced or imprinted.
Okay.
And right next door, there are other genes that are only active on the maternal copy. The paternal copy of those is silenced.
So for that whole region, you absolutely need one working copy from dad and one working copy from mom to be healthy.
Exactly. So if you have a deletion on the chromosome you inherited from your dad, you lose the paternal-only genes. You have no backup because mom's copies were already turned off. The result is Prader-Willi syndrome.
And if the deletion is on the chromosome from mom?
If the deletion is on the mom's chromosome, you lose the maternal-only genes. Most importantly, a gene called UBE3A. You have no backup because dad's copy of that gene is turned off, and that causes Angelman syndrome.
It's like you have two different keys on your keychain, a dad key and a mom key. If you lose the dad key, you can't open the Prader-Willi door. If you lose the mom key, you can't open the Angelman door.
That is a perfect analogy. It shows that our genome isn't just a list of ingredients. It's a very specific recipe with instructions on who adds what and when.
Let's zoom out now for our last section, section 6, the bigger picture. We've been talking a lot about these single gene or monogenic disorders, but Robbins makes a point to emphasize that the diseases that most people in our society actually suffer and die from, diabetes, hypertension, atherosclerosis, they aren't single gene disorders.
Right. These are complex multigenic disorders. They are polygenic.
Meaning many genes?
Yes. There is no one diabetes gene. There are hundreds of small variations in the genome polymorphisms, or SNPs, that each add a tiny whisper of risk. One variant might increase your risk by 1%, another by 2%.
And Robbins uses the concept of the threshold of liability to explain this. I like to imagine this as a bucket.
That's the standard and best analogy. Every one of these little risk gene variants you inherit is a drop of water in your bucket. Some people are lucky. They inherit a bucket that is nearly empty. They have a low genetic risk. Some people, just by the luck of the draw, inherit a bucket that's already half full.
But the bucket isn't overflowing yet. They aren't sick.
Not yet. But then comes the environment. A poor diet, a sedentary lifestyle, stress, smoking. These are like pouring big cups of water into the bucket.
Ah, I see.
If your bucket was already half full because of your genes, it doesn't take much environmental water to make it overflow and for you to develop the disease. But if your bucket started out nearly empty, you can tolerate a lot more bad lifestyle choices before you get sick.
This perfectly bridges that gap between genetics and lifestyle. It explains why your Uncle Bob can smoke and eat bacon every day until he's 90 and be fine, while his neighbor does the same thing and has a massive heart attack at 50. Uncle Bob just had an emptier bucket to start with.
Exactly. And it's empowering for the patient. You can't change the starting level of water in your bucket, but you absolutely have control over how much more water you pour into it.
And we can't finish without just briefly mentioning the large-scale chromosomal disorders, the big physical errors in the blueprint?
Right, the things we can see on a karyotype. Trisomy 21, or Down syndrome, is the most common. It's usually caused by a non-disjunction event. The chromosomes fail to separate properly during meiosis, the creation of eggs or sperm. And as Robbins points out, the risk for this increases dramatically with maternal age.
And the sex chromosome disorders as well.
Klinefelter syndrome, which is XXY, these are males with an extra X chromosome. They tend to be tall, have hypogonadism, and are often infertile. And then Turner syndrome, which is 45, X females who are missing an X chromosome. They characteristically have short stature, a webbed neck, and cardiac defects. These are errors of the entire library, not just a typo in one book.
Underwood wraps this all up with a discussion on diagnostics. How do we actually see these different types of errors?
The technology has just evolved at an incredible pace. We used to only have karyotyping, literally taking a picture of the chromosomes under a microscope. That's good for seeing big things like Down syndrome. Then came fish fluorescence, in situ hybridization, where we use glowing DNA probes to find specific small deletions. Then PCR, which lets us amplify tiny bits of DNA to find specific sequences.
And now?
Now we have next-generation sequencing. We can read the whole code. We can find those tiny single-letter point mutations we talked about at the very beginning. We can screen a patient for hundreds of different genetic diseases at once from a single blood sample. It's revolutionary.
And finally, a word on epigenetics. Underwood highlights this as the future.
It absolutely is. It's the software layer on top of the hardware. If your DNA sequence is the hard drive, epigenetics is the operating system. Things like DNA methylation and histone modification determine which programs or genes actually run in any given cell. This is what explains how a liver cell and a brain cell can have the exact same DNA, but look and function completely differently.
And as we saw with the Barker hypothesis, these epigenetic marks can be written by the environment.
That's the critical link. Our experiences can change how our genes are read.
So we've gone from the single-letter typo of sickle cell to the structural collapse of Marfan, the metabolic traffic jams of the lysosomal storage diseases, the stuttering genes of Fragile X, and finally to the complex bucket filling of diabetes.
It is quite a journey, from the micro to the macro.
So let's land the plane. What does this all mean for you, the listener? What is the clinical so what of all this?
It matters because the mechanism dictates the treatment. If I know a disease is caused by a missing enzyme, like in Gaucher disease, I can actually give the patient that enzyme through an infusion. That's enzyme replacement therapy.
Okay.
But if I know a disease is a receptor problem, like in familial hypercholesterolemia, giving them an enzyme won't do anything. I need to treat the downstream effect. I need to lower their cholesterol aggressively with drugs. If it's a structural defect like Marfan, I can't fix the gene yet, but I know I need to medically manage their blood pressure and monitor their aorta with imaging to prevent that catastrophic mechanical failure.
And understanding the inheritance pattern dictates how you counsel the family.
Exactly. Being able to tell family, this is an autosomal recessive condition, there's a 25% risk for your next child, versus this is a mitochondrial issue, so all of your children are at risk, but the severity is unpredictable. Changes lives. It changes reproductive decisions and family planning.
We started this whole deep dive by asking if genetics is destiny.
And I think what we've seen time and again is that it's actually probability. Even with a hardwired mutation, things like incomplete penetrance, variable expressivity, and all those environmental modifiers come into play. It loads the dice, but it doesn't always determine the role.
Here is a final provocative thought to leave you with. We typically think of our genome as a fixed inheritance from our parents, a dusty old book that we're given at birth and we can't edit. But with what we now know about somatic mutations, those acquired errors that Underwood talks about, and the shifting landscape of epigenetics, are you genetically the same person today that you were when you were born?
That is a profound question. Your germline DNA, the blueprint in every cell, is largely the same. But your somatic genome, your functional genome, it's a living mosaic of scars, errors, adaptations, and epigenetic changes. You are, in a very real sense, physically writing your own biological biography into your cells every single day. Every sunburn, every meal, every stressful event writes another line in that code.
A biography written in DNA. Thank you for joining us on this deep dive.
My pleasure. It was a great discussion.
And for those of you who want to see the diagrams, especially those inheritance pedigrees and the mechanisms of non-disjunction, open up Robin's chapter on genes and human diseases and Underwood's chapters on what causes disease. It's absolutely worth the read. We'll see you next time.